Eres acción que transforma. Explora el mundo y haz lo tuyo. Responde a tus inquietudes, abriendo posibilidades. Crea a través de tu talento, convirtiéndolo en baile, en música, en una expresión viva. Innova con conocimiento y determinación, buscando soluciones, impulsando tu vocación. Emprende tus ideas, dándole vida a tus sueños, convirtiendo tus planes en hechos. Lidera para transformar tu entorno, aplicando tu conocimiento y generando cambios sociales. Comparte el espíritu ágil. Vive UPAEP, la Universidad Transformadora.
Hello everyone, welcome to our last day of our STEAM week. So far, it has been an insightful reflection about the impact of science, technology, engineering, arts, and mathematics on our academic development, but also in our daily lives. Our previous speakers have shown us how important it is to reflect on these topics nowadays, and actually why it is worth to celebrate science, technology, and all the acronyms of STEAM, because those are the right pathway to make a better world. Although we have divided the different acronyms in each day, obviously the previous speakers have shown us that those are always interconnected. And that is the root of the value of STEAM in our lives. Today, we close with a flourish. We have Elyse Fosse from NASA. It is just backstage, we have been discussing how busy she is in NASA. Can you imagine someone from NASA right here with us in Prepa UPAEP? Let me read something about the story of Elyse in NASA. Elyse is a system engineer in the Jet Propulsion Laboratory who currently works on Mars Sample Return Lander, as well as Mars 2020. She has worked on Mars 2020 since early 2014, and she has had the opportunity to work on the two teams, one that designs and tests the Mars 2020 rover, and one that operates the Mars 2020 rover. Prior to Mars 2020, she worked on infusing new technologies into the systems engineering process. Currently, she is the lead mission planner for the Sample Retrieval Lander, and she's helping to design the operation of the mission to ensure that samples are gathered and launched from Mars in time to rendezvous with the Earth Return Orbiter. So, Elyse, thank you for being here with us today. It is a great pleasure to have all your experience and to be shared with our students. Thank you for being here, Elyse. And the floor is yours.
Great, thank you so much for having me. So I'll go over to my presentation. So what I'll be talking about today is all of the great exploration we've done with our Perseverance rover on Mars. And I'll walk you through what it actually means to actually operate something that is on an entirely different planet. So first, a little about me. I grew up on the East Coast, so I went to high school in New Jersey. And then I went about 4 hours north to Massachusetts to study mathematics. And then after traveling a little bit, I decided I wanted to go to grad school and made a big jump to fly out to California and get my master's in mathematics. All throughout that time, I didn't realize an opportunity at JPL or working for NASA would be a possibility for me. I grew up loving science fiction, loving Star Trek and Star Wars, but always thought it'd be a point of entertainment for me and not an opportunity for me in a career. But luckily, I was able to get an internship at JPL in 2009, and I was able to start working on the Perseverance rover in the summer of 2014. Back then, it didn't have a name, so we just called it Mars 2020 for the place we were going and the year that we were going to launch. And I had the great opportunity of working on Mars 2020 throughout development, so helping to design the system, helping to test the system. And then I've been helping operate it since we've landed in February 18 of 2021. So it's been over an Earth year on Mars, which is very exciting. First, I'll give an overview of actually what Perseverance is and what we're doing on the surface of Mars. So first, we landed. That's always an exciting time. It's not a given that we'll land successfully. It's very nail-biting to basically drop a parachute and then a powered descent with thrusters to safely land something that is about the size of a Mini Cooper on a different planet. That's definitely a feat that we strive to be successful at, but are not always successful at. But we were this time. So February 18th, 2021, we landed in the Jezero crater on Mars. And it's a place where scientists believe was an ancient lake or river system. So it looks very much like what dried out lakes on Earth look like. So scientists find those interesting. And what you're seeing here are first images that humankind has ever made as part of a landing. So when we landed, we not only had cameras looking up at the parachute as well as down at the rover, but we also had looking down at the surface of Mars as well. We had never achieved something like this before. Before, what we would get is we would get confirmation via data. So essentially like a text message from the rover telling us it landed. Whereas this time we got to see the images showing us that the parachute worked correctly, that we were landing on Mars. And it still gives me chills, this image of the rover it's still attached to the descending vehicle, and all of these wires will get cut away and it'll gently place itself on Mars. And these kind of swoops are actually plumes of the Martian surface moving away. It's still exciting, and it's still kind of surreal that we were able to achieve that. And then why did we choose Jezero Crater? So what we see here on the left is this is actually imagery taken from an orbiter that's been orbiting Mars for years now. It's from an imager called HiRISE, and it gives us a lot of data about where we're landing before we land. And what scientists found interesting is the fact that they think it's a riverbed or a lake bed. So they believe that billions of years ago, there was water here, and that water was flowing, so active flowing water. And why that's interesting is why we go to Mars is because Mars looks a lot like Earth. You know, you see pictures and it looks like some desert scenery that you would see on Earth. And for scientists, what that means is it might mean that Earth and Mars had the same shared history, and then at some point that history diverged. So why did Mars all of a sudden lose its water? Did Mars have past life that perhaps we still have signatures of on there? That's why we go back, because we want to understand if we can confirm our theories of how Earth evolved. If Mars has the same evidence, then it's a better story as to how Earth evolved as well. So what we're searching for are biosignatures, which are things that show that there was signs of past life. And here's an example down here of something that we see in Australia. Australia has the oldest rocks on Earth. So if you ever want to see old rocks, Australia is where you want to go. And what we do is we see the biosignatures on those rocks, and we're trying to search for those same types of signatures within this crater. And we're doing that with this fantastic rover that we call Perseverance. So I'll walk you through all the science instruments that we have that are helping us do this. So ideally, as a scientist, the scientists would want to be physically placed on Mars and look around and do what they do in order to understand the environment. But unfortunately, we can't do that yet. We're not able to do human spaceflight. So instead, we set a highly capable rover that tries to replicate the type of science and the type of observations that a scientist would want to do. So the first thing a scientist is going to do is they're going to want to look around. They're going to want to use their eyes. And because of that, we have numerous cameras on the system to help us understand what's going on. We start with Mastcam Z, which is a zooming. So we have this mast here, and we have a camera sitting up here that are basically our eyes. That would be Mastcam Z and SuperCam. So these are ones that can look around and kind of take your landscape views of what's going on, but also have the ability to zoom in super tight. And then SuperCam also has the ability to shoot lasers in order for us to see how the ground reacts to that laser pulsing. Who doesn't want lasers for eyes? I'm just saying. And then on the arm over here, we have two cameras, the Watson camera as well as Pixel, that we are able to place very close to the ground, about a few centimeters off the ground, to help us understand the makeup and get really up close to see it. And the advantage of the Pixel instrument is it actually gives us X-ray vision, which is very useful as we're trying to determine which samples to take on Mars. So once we understand the makeup with our eyes, then scientists might decide that they actually want to take samples. One of the primary objectives of Perseverance is to obtain 30 samples and leave them on the surface of Mars for a future mission to bring back to Earth. And so this is a multi-year, multi-billion-dollar mission in order to bring these samples back to Earth to get them into scientists' hands here. That way they can use their high-tech equipment in their laboratories to understand the makings of the soil and to make their observations. What Perseverance is doing to achieve that is we're using our cameras for close-ups, and then once we decide that a rock is useful to drill, once science decides that, us engineers help them how we're going to drill. So on this end of the arm, it can rotate, and we can either use Sherlock or Pixel, or we can rotate and use a drill to take coring samples. Once we core into the surface of Mars, we're then able to deposit that within the internal belly of the rover for it to sit and wait for us to drop it on the surface for that future mission. So right now we have 7 samples sitting inside the belly of the rover. And actually today, after I talk to you, I'm going to go into operations and we're going to attempt and plan to collect the 8th sample today. In addition to all of that wonderful sampling that we're doing, we actually have other science instruments. We have a weather station on Mars named META. And so this is a way that we can understand the temperature on Mars, the wind speed and direction, the humidity, as well as pressure. And we actually just went through a series of dust storms where META helped us and other missions understand how intense those storms were and whether it was safe to drive and to take imaging. On top of that, we have RIMFAX, which is a ground-penetrating radar. So as we drive to get to our new sampling locations, we actually penetrate the surface of Mars and take this radiometry in order for us to understand what the underlying makeup of the Mars stratigraphy looks like. And then finally, we have MOXIE, which is what we call a tech demo. So there's the science that MOXIE is doing is proving that we can generate oxygen from the Martian atmosphere. And we've run it 3 times already, and it has successfully generated oxygen each time. This is very exciting because if we actually want humans to go to Mars, we need to figure out ways to provide them oxygen. We can't bring everything with us. And so this is a small but mighty tech demo where right now it generates the oxygen, but it just puts it right back out into the Martian environment. We're not storing it for any reason, but it's showing that it's feasible, that it's something we can do for future missions. So where have we been so far? Well, we landed up here in the Octavia E. Butler landing site. We call that Sol 0. So a Martian day is slightly longer than an Earth day. It's about 24 hours and 48 minutes. So to not confuse ourselves, we call those Martian days sols. And we started here on Sol 0 at the landing site, and we've slowly started our traverse around and down the delta. And this blue spot is where we currently are. As you see, we kind of are doubling back now, and that's at the request of science, as they think they went as far as they want into the delta, and now they'd like to start working their way back and moving on to a next part of the mission. What you see over here, where it's more zoomed out, is anything in gray is actually that high-rise imagery, so it's coming from a different orbiter. So this is what we saw before we landed, and now as we're landing, now we can see, well, how deep are things? How interesting is it? And can we actually drive it, or is the slope more than we thought it was going to be? So it's always a case of Mars is going to be Mars. We try to understand it as much as we can. We try to study it as much as we can, but at the end of the day, when we land and we start operating, it's a different environment, and we have to react differently from our expectations and divert from them, because all of a sudden we have more information that shows us that it might not be safe to drive, or it's not as interesting as we might thought, and this other place is more interesting. And so in doing that, I'll now walk you through what a day in the life of what we do on the operations team is. So first, I want to point out these storyboards that we have here, I did not create. These are storyboards that graphic designers at JPL helped us create during our design phase. A lot of our job in designing before we operate the rover is explaining how we're going to operate it and explaining why it will be successful. And in order to do that, we've used graphic designers to help us tell that story. Because I'm good at PowerPoint in terms of putting words on the page, but in terms of making useful illustrations that explain things, that's something where an expertise of a graphic designer is very useful. So what we start out with in our day is we review what we planned yesterday. What did we do yesterday? And then what were we planning on doing for the next few days? Did we drive yesterday? Did we take a sample? What are we planning to do? Are we continuing to drive to a sampling site, or are we already at a sampling site and we're choosing to sample? An example is today, we're at a sampling site, so we'll be choosing the sample, but over the next few days, we'll probably be driving away towards a new site. And this is all involving science and engineers. So the engineers are worried about the health and safety of the spacecraft, and the scientists are trying to maximize their science goals and objectives in their experiments. And so we work together to make sure that we're making a plan that is safe, but that is also achieving the objectives that science want at the pace that they are expecting. Once we understand kind of the overview of what we're doing, we wait for the rover to send us the data. So basically what we're waiting for is we told it what to do the day before, and now we want some information back from the rover to confirm that it did what we expected it to do and that we're okay to move forward with our nominal plan. If it comes back and it says, hey, some things didn't work, that's okay. We start working what we call those anomaly paths, and we work towards recovery. But it just means we wouldn't be on our nominal path for that day. And now not every day is exciting as touchdown, but this is what a downlink assessment looked on the day of landing, where we were waiting to hear if we had successfully landed on Mars. So what everybody was looking at there is they have these computer screens up that are basically looking at data being streamed directly from the rover on Mars, and it's telling us that it's okay. This is before we even got images. This is essentially just data back, like text messages saying, I'm okay, I'm okay. And it was very exciting because this means we now had a job to do. So once we get our downlink assessment, we review the science data. So what science have we done? And then we just decide what the rover does when it wakes up the next morning. We typically try to plan when the rover's asleep. It doesn't quite always work out that way because we're not following Mars time. So we're not making our day 24 hours and 48 minutes. We do that in the beginning, but at this point in the mission, we're not. But we do try our best to schedule things or plan while the rover is asleep. It's recharging its battery. So once it wakes up at sunrise, we're able to send data and give it its instructions for the day. And what we're doing here is we're actually selecting science is selecting targets. So where do we want to point the cameras? Where do we want to shoot the laser? Do we want to go close to the surface with some of those other science instruments and interrogate? And they work that with the folks who we call the rover planners, who are concerned about the safety of the arm, how can we move it? And they also are concerned with driving. So here's an example of while we're planning things on Earth, we actually have animations that show us what we expect to do. So this is a simulation that we have, and this is a drive day. So this is a case where during operations, the rover planners are showing us how they're planning on driving and what pictures they're planning on taking. You could easily see that perhaps you could do this just by explaining what the drive is doing, but having this type of visual capability enables us to better understand what we're doing. Now you can see, oh, this is the orientation where the rover ends. This is where the sun will be. This is where the wheels will be pointed, versus having to ask all those questions. The visual interpretation is much more what we're used to trying to understand as we do movements. So once we understand the plan for the day and everything looks good, we generate what we call the uplink products, which are the series of commands that we group into sequences and any files we need. We validate those. So they run through a series of basically rover simulators, just software only, so no hardware. We're not trying to move anything, but we're simulating the software to make sure everything should work as expected, and we review that. And then the final step of the day that everybody loves is we all go around and we give a go. So anybody in the room can say no at any point in time because they have concerns about the safety or the pedigree of the science we're doing, and we will go back and rework those issues. So everybody has a say as to what we're doing. And when I mean everybody, it means usually in the room right now, we have about 12 people, but then on the line, we have about 30 to 40 scientists each day who are helping construct these plans. And these scientists are coming from all over the world. We have instruments from all over the world, and then scientists. It's an open call to participate. So you don't even have to have participated in the construction of the science instrument to help us decide what we're doing on the surface of Mars. So once we've done that go and everybody's happy, we release everybody, and then we send the file over to the Deep Space Network. And the Deep Space Network uses a series of satellites to communicate directly to the rover on Mars and to send our plan. So we bundled it up and it's ready to go. We send that via the satellite directly from Earth to the rover, and then the rover starts its day. So what I'm going to end with is talking through some significant operation events that have occurred since we've landed on the surface of Mars. First, we landed. So this is the first entry, descent, and landing image we saw. So this is part of that downlink assessment that we were talking about. After we all cheered, we then started seeing these images come in. And this is the first image ever we saw of any rover landing on the surface of Mars. It's just still exciting, and so it's still awe-inspiring. And then, like we mentioned, we planned our first drive. So we had already showed this same simulation to talk through how we simulate, but this was actually the first drive we did on Mars. So we drove a little bit further. We took some pictures before we continued to drive, and then we eventually turn around. And what you see here is where there's that grid where it doesn't look like a Martian surface. That's just places where we don't actually have data. So we didn't have data there because the rover was already there. So we couldn't take pictures underneath it. But now the rover has driven onto what we call the mesh, which is basically imagery of the surface of Mars that we've taken. So we understand the height of the rocks and the slope, so it's safe to drive. So that's what we looked when we were planning. And then in the downlink assessment, this is what we saw. So here we did this drive forward and we did that turnaround, and we see our wheel tracks. We even see that we went over some rocks here, which is great. And what you're seeing here is the front of the rover with the arm tucked in, and it's looking backwards towards where we drove. So this is a great example of what we planned for that day is exactly what happened. And some of that is because for these first activities, we actually planned them months in advance. We didn't wait until the day of. Nowadays, when we operate, we don't plan what we're doing until the day of, and we have about 8 hours to plan it and send it up to the vehicle. When we were first starting, we knew we were trying to understand what Mars is like and how this rover is going to interact with Mars. So we did some strategic work and did some prep work, but it's always, you never know until you get to Mars how it's going to interact. The next thing we did is we did a robotic arm checkout. So once we proved that we could drive, we then wanted to make sure that our arm moved correctly. And so what you're seeing here is another simulation. So this is a ground-based tool that the operators use to confirm that the commands we're going to send are going to move the arm as we expect. So we call it an arm because it looks like an arm and it has joints like an arm. So it has a shoulder joint, an elbow joint, and a wrist joint. And what you're seeing right now is we're rotating the wrist. Now we're rotating the elbow. So it's almost like we're going to the doctor and we're doing a checkout. And we're doing that because we just landed. So we want to make sure that all the mechanism survives landing safely and that it's safe to use all of these instruments. So we'll let it go through. Oh, finishes. And then here's what we wound up doing on Mars. So first we have this picture. Well, now we see that the arm is out, and this instrument, the white box, is Pixel. So it's one of the science instruments looking at us. But now we see it's raised off of the dock or the station of the rover. And we can see that, I love this, imaging is great, is we can see that the sun is right above it. So we get this great shadow of Pixel. And then on the right, we see those same wiggle motions that we saw in the simulation actually happening in real time on Mars. And we do this because we have those cameras that are on our mask that are kind of our eyes. And so we use those cameras, Mastcam Z and some of our engineering cameras, to help us make these pictures and to construct them. Because one, they're great to share with the public. And two, they're invaluable for us to understand what's actually going on the surface. In addition, I don't have a great video of this. We actually have 2 microphones on the surface of Mars with us. One was used to capture the sounds of landing, and the other one is used to capture the sounds as we're moving our mechanisms. So this goes into a great place about debugging. Science enjoys it because they get to hear the wind and they can correlate that with the weather station data. As an engineer, what we enjoy is, if your car is broken or if something's wrong with your car, the first thing you hear is you hear something wrong. You typically hear a clanking sound. And now that we have a microphone on the surface, if we think something is going wrong, we can record audio data and understand and correlate that with what we hear with our test bed, our hardware that we leave on Earth that we still test with, to see if it's correlating that something's going wrong. And that's going to be invaluable. Luckily, we've had no issues where we've needed to take such data. We have been taking microphone recordings, but they've all been great and nominal, and they've been what we expected to hear, which we're A-okay with right now. And then after we did all of this, we now have to remember that we have a helicopter on Mars. So the Ingenuity helicopter hitched a ride with us, and it was located on the bottom of our rover. And before we could do much driving, we needed to deploy it. And so what you're seeing here is the series of pyro firing. So we did small explosions on the surface of Mars to drop the helicopter down such that we could drive away and he could actually start flying. So again, this is a great example of imagery. So we're using our arm to put it underneath the rover to take these types of images to confirm that the helicopter worked as expected. This is another type of operations where we did plan that months in advance, particularly because the helicopter team is a separate team from the operations team. So we needed to work with them to correlate what they wanted to do with how we nominally do ops. And then we had our first flight. So this is a series of images taken from Mastcam Z, the camera that's sitting on the mast. And what it's going to show is the helicopter spinning up, and then it's going to take a lift off, and then it's going to land right back down. So what we're seeing here is this is the first time humans have ever flown on another planet. That's amazing. It's 2021, and we have now flown on another planet. What makes this so exciting for me as an engineer is it means when we go to research and we go to other planets, it's no longer, oh, we can put things in orbit around it or we can drive. We can now have these satellites of helicopters that are flying around, doing science for us and scouting it. What's nice about that is they're lighter. They don't take as much to lift off from Earth and to land. And so it really opens up the possibilities of how we can do space exploration in the future. What you see here is basically once the helicopter had a successful flight, we wanted to make sure we didn't lose contact with it. It has to stay close to us because its only way to talk to Earth is through Perseverance. And so we have our drive path, and then the green line overlaid it is the heli flights that have brought it to us. And the red was the planned flights. We're at flight 21 today, but this was taken at flight 9 where they were planning to go. And what's interesting in one of the exciting parts is it is now scouting for us. So instead of us relying only on those orbital images from the high-rise camera that are black and white and don't really show us depth very well, we now ask the helicopter to go fly ahead of us, and it will take images that'll show us better the terrain, which allows us to map out our drives faster and in a safer way so that when we get to actually executing those drives, there's more probability of success. So it's a great opportunity of seeing all these different technologies working together in order for us to achieve a really fantastic mission. And then we went and we finally did our drilling on Mars. So this is where we're taking our first samples. And how we take these samples is on the first day, what we do is we abrade. So we don't fully take a sample, but we use an abraded bit just to drill slightly in to see what is the makeup of this rock. Science finds this rock interesting. Let's just toe dip a little bit and see, is it as interesting? Is it going to crumble on us? Is it amenable to actually taking a sample? And once we believe it's amenable, then we actually go ahead and take that sample and we drill in and we take a core. And then what's left on the arm of the rover is the drill bit with the core inside. And this was our first drilling. So everything came down. We got the downlink assessment, which is essentially those text messages telling us, you got a sample, everything's great. And then we were waiting for the images. So we get these images down and it's empty. So we didn't know where the sample went. Everything told us on our rover, Perseverance was telling us everything went fine. We were healthy, we were safe, and we got a sample. But all of these images are showing no sample. So where is it? So much like what happens when you think you dropped your keys is we looked all around. Maybe we dropped it somewhere. We took all these images, we looked around, and nothing was there. There was nothing in the sample. There was no little pillows around where maybe it dropped out as we extracted it. There's nothing underneath the rover that maybe the wind blew it. It was just gone. And what we wound up doing is we took a nighttime Watson of the borehole, so that the borehole is what we call the what's left of the core once we sample on the Martian surface. And Watson is one of those imagers that we can put close to the ground. And what we see is we see the striations, so we see the indents of where we took the core, and we see this little nub of rock here. So what we believed happened is Mars was Mars, and Mars didn't behave as we expected. And this surface was actually more crumbly than we had expected. And when we went and took the core, it was not solid enough to stay in. So once we pulled out, it just fell back in and kind of collapsed amongst itself. So while we did achieve our first sample on Mars autonomously, so we took the sample and we held it there without any human intervention, we didn't wind up capturing that sample, which helped us understand a little bit more about the makeup of these rocks. And it is a great indicator of Mars is always going to be Mars. As much as you think you know about a problem, as much as you think you can understand it, you should always expect you're going to discover something new. And that's what keeps it fun and interesting. So finally, on Sol 190, we actually do have a successful sample. So this is what a good successful sample looks like, is you look into that core bit and you see it full of rock, which is exactly what we want. Scientists have looked at this and they found it interesting. And this is what we're stored currently in the belly of the rover, 7 of these samples waiting for it to be dropped on the surface of Mars for our future mission to pick up. The last picture I'll leave you with is a Mastcam-Z mosaic. So what that really means is we like to take selfies with our rover. But unlike on Earth, where our selfies are really, we can just point and click, it's a lot more work on Mars. So what you're seeing is every tile that's being added is actually a picture we're taking on Mars with our MAST instrument, with Mastcam-Z. So it's going around and taking these series of pictures. And then on the ground, we receive these hundreds of pictures and we stitch them together in order to, sorry about that. We stitch them together in order to make these selfies. And so when we're doing this in operations, this is a series of hundreds of images that we need to command and then validate that the commands are safe and convince ourselves that it's okay to do. And luckily, these are very reusable. So we're able to, once we've done these once, which we have, we're able to take these off the shelf essentially and put them into the plan so that way we don't have to spend a lot of time simulating or understanding if it's safe to do, because we've done it before on Mars. We now understand it's safe. And so as you see, it'll keep going around and finishing. It'll leave the center black because it actually can't take a picture of itself in that way. The MAST instrument, we actually need to use our arm to do that. So we take these series of instruments with Mastcam-Z to get the surrounding, and then we use the arm, much like how you take a selfie yourself, to take the picture of the actual rover, and then we stitch those together. And that's how you wind up with an image like this. So this is an image where Mastcam-Z has taken around and done all the imaging of the top of the rover, and then we've put our arm out, and we took one image where we were looking at the helicopter and then one image where we're looking at the picture, and we've combined those together to make this one. And this was done right after helicopter deployment. So we had deployed the helicopter and then driven away, as you see with our wheel tracks, and then turned around to take this family portrait, as we like to call it. The last thing I'd like to point you to is we do have this website, mars.nasa.gov/Mars2020. You can see all of our images. What we do is we have a raw image pipeline, which means within 24 hours of us taking these images on Mars, they are released to the public. On top of that, we have our nice little weather service, Meta, that actually tells us all of the temperature on Mars and the weather system. And so we have nice little dashboards on the website that'll show you that, as well as give you some blog posts that go into more detail about all of the experience I've talked about, as well as a little bit different experiences of how other folks experience operations on Mars, or how they've encountered difficulties with Mars being Mars and how we engineer and how we've encountered and dealt with that. And with that, I will say thank you for your time.
Thank you, Liz. It has been an extraordinary presentation. Thank you so much. I'm sure all of our students and all of the audience have enjoyed the presentation. I have different questions from our students, but also from myself. And the first one, I think it's very complicated for regular people like us to understand how much is involved in this resources, work, time, but also it is very difficult to understand the benefits that we can get from it. So what would you say it's the impact that this project can have on our regular daily lives?
That's a great question. So I think there's a couple things why I love working at JPL and why I love this mission. The first is the science impact. Scientists are still trying to understand how Earth evolved and what was our starting point. And because Mars is a great analog, we always go to Mars, or we have at least for the past 20 to 30 years. But we've never been to bring samples back in order to let scientists have it. And what that means is it's a better, it means anybody on Earth who has the right credentials can now get those samples. And this mission is the start of that. We're able to take those samples. And then the next mission that I'm working on is the one that's going to bring it back. So from a science perspective, that's great. From a humanity perspective, it's cool to see a helicopter fly on Mars. It's just cool, and there's just something about that excitement of finding something you're excited about and being able to work on it, whether that's engineering, whether that's science, whether that's art, whatever that passion is. When you get a group of passionate people together, it is amazing and astounding to me what we're able to achieve. So less about the science and the metrics and more about it's just inspiring and it's exciting to see. And, my generation has that thought up the helicopter and that helped with this rover. Who knows what the next generation is going to think up about in terms of space exploration and what they're going to be able to achieve. And we're always standing on the shoulders of each other. And that's a really important thing. We don't do this in a vacuum, and no one person can do what I've just shown you. It takes a team. It takes a numerous amount of people who are very dedicated, who have integrity and are willing to make the tough decisions and to accept the mistakes and move forward. And that is also very encouraging. When you can see a group of people work together like that, you really can see that like we can do pretty much anything when we want to, when we put our minds to it.
That is very interesting because you have mentioned several times about the importance of teamwork, and that was actually one of my questions because also perseverance is a meaningful name. So what would you advise youngsters in terms of resilience, commitment, motivation, teamwork?
I think I'll start with the bad news. It's not easy. When I was in high school and even in college, I thought my dream job would be sitting in a cube with nobody around me doing math. I did not think I was a team player. And I slowly realized that that's not going to get me very far, and it's not going to be a lot of value because when you do work in a vacuum, guess who congratulates you? Nobody, because nobody knows you did it. And also when you have problems, who do you bounce your ideas off of? There's no one to bounce your ideas off of. So while perseverance and resilience are really about you will set your mind out to do a goal. And even though it's the thing you want to do, there will be roadblocks and they're going to be unexpected because if it's something you want to do, you're going to probably think about it. You're going to understand how your path forward is to get from step A to B to C, but you're not going to know that step Z is going to just come in out of nowhere and you have to deal with it. And so a lot about the teamwork is relying on your teammates to help you with those unexpected problems. I am not the smartest person in the room. I never plan to be. I plan to be surrounded by very smart people and that I can ask them the questions. I don't want to be the expert. I want to know who the expert is and ask them those questions. And I want to make sure that they trust me, that they can answer it honestly, because sometimes they give me answers that I don't really want to hear, such as we can't do what you want to do. But that's okay. We can figure it out and we can move forward. So I think out of all of that, the biggest thing is patience. patience with yourself as well as patience with other people. I struggle with patience with myself. I think I should know things immediately. I should be able to figure it out. I should have this solved by 5 p.m. and I should be home having dinner at 7. And that's just not how the world works. And that's not how anything works if you're exploring a different planet. You have to have patience that you might have approached the problem incorrectly in the beginning, and you might need to back up and then come back in and approach it differently. But each one of those setbacks is another way that you've learned, so that when you encounter your next problem, you're going to know better, you're going to learn better, you're going to understand yourself better as to how that problem to begin with in a different way to help you get to that solution.
Thank you. Thank you for highlighting that importance of it's not only about science, it's also about teamwork, about collaboration. Thank you for that. And actually, I have some questions for our students. And one of those is very interesting because it says that, why did you choose a master's in mathematics if you are doing such a practical job at NASA? Because students are really scared about mathematics. It's not very popular nowadays. So what would you say about that?
So math, this is the very honest truth, is because I liked being right. And I liked knowing if I was wrong. I liked that somebody could show me why I was wrong. And so that is why I always strove to do math. But I was struggling with that problem when I was getting this master's in math and even in my undergrad, because I also knew that I thought my career opportunities were very limited. I thought it would be biomedical statistics, which is but to me, it looked like you would be doing the same thing every day. So it wasn't really exercising my creative muscles as much as I wanted to. But what I did know about getting the master's in math is it was fun to me. I'll own it. I like math. I enjoyed it. But it also, I think what it brought to my job at JPL is I approach the problem differently because I don't have the same backgrounds. And at first that intimidated me if I felt that I was not worthy of this job. But it only took me a couple years and great team members to realize I'm bringing that added value of I'm thinking about this problem differently. I break it down as if it's a math word problem. So I'm like, well, what do I know and what do I don't know? And how do I understand it? Versus other people who have more expertise, we're relying on their gut feelings more. So those two things combined, we're helping us get to a better solution. Apologies, the lights are going off.
It's okay.
We're helping us get to a better solution. Would I change it and go get an engineering degree knowing what I know now? Probably not, because I still got the degree I wanted. And I knew once I got to JPL, once I got the internship, I knew that this is a place I wanted to stay. And how I got the internship is because they needed mathematical analysis for a mission that was in concept phase. So they were doing research and they needed somebody who knew a very specific math program to help them solve this problem. And so getting the degree and staying true to what I thought I wanted to do, or at least what I enjoyed and was passionate in, had me wind up where I wanted to. So I think it worked out.
Yeah, well, there it is. So for all kids that are watching this conference, go for math. You can, creating great projects just like Elyse. I have one more question. It's about the evidence of past life on Mars. If you guys identify those evidences, what impact would you say that can have in our understanding of universe?
Oh, so much. I do want to go back to the last question before I leave it, is I want to be very clear with my math degree. I wasn't always good at it. My first college class, oh, now it got really dark. My first college class, I got a 45 on my first exam out of 100, not out of like 50. Like I failed it horribly. Now I'm going to shake. There we go. Yeah. I failed it horribly. And I had to come to terms with that. But it goes back to perseverance and resilience. Is I knew this is something I wanted to do, and I just had to approach the problem differently. I didn't study for that exam correctly. And I worked with the professor. I asked for the help, and then I was able to graduate with honors. So just because you like doing something does not mean it's going to come easy. And that's a mindset that I think is useful to keep in mind. Going back now to the signs of past life and the impact, we have these knowledge that the universe was created out of this big bang, and out of that we have these planets. but we have gaps in that timeline. So if you open your science book, you'll see a timeline and it'll say Big Bang, Earth, Mars. But in between those things, it's not very clear what was happening. And scientists have ideas about what happened, but as good scientists, they call those ideas hypotheses. And then they want experiments to confirm their hypotheses or to disavow those hypotheses and show that they're incorrect. So these biosignatures will help us confirm their hypotheses because they've seen things on Earth with the oldest rocks here in Australia, and they've created some hypotheses. And now they're like, well, if that hypothesis is true, then it should also be true on Mars. So if we see those same biosignatures, we see those same patterns, then that would confirm and help us understand and weave together the history books for how Earth evolved, as well as potentially tell us, why did Mars not survive and Earth did? Mars such a contentious environment, but Earth isn't. And hopefully that might help us understand, how do we keep our planet safe and secure? How do we help prevent climate change? How do we preserve this resource that we have? And how do we continue to explore future planets to understand more about our history?
Well, that's very interesting. So, and one final question for you, Elyse, and it's coming again from one of our students. It's how difficult the communication is between the rover and Earth. Can you elaborate a bit about this? How long it takes, for example, for data to be gathered and then communicated to Earth?
That's great. Yeah. So when we land, we call it 7 minutes of terror. And that's because it takes 7 minutes from the rover actually landing for us to actually get that information back. So there is a lag. So it's almost like, I don't even know, never mind. It's going to be too old for everybody. But so what we do now is we have 8 hours to plan what we're going to do on the surface of Mars. We then send that to the spacecraft. It takes about, I want to say 20 minutes to send to the rover. And then it takes another 20 minutes for us to get the confirmation. So the rover is going to go off and do things. We don't ask it to wait, but it'll take us about 40 minutes to hear that it actually worked or not. And then throughout the day, it'll start talking to us to tell us to send out more data, the images and more of those text message information to tell us what's happening. Those can take anywhere between 1 to 4 hours to come back to Earth because of what we call latency. So it's not only the distance of Mars and Earth, but it's also we're using orbiters to do that communication. So those orbiters have to turn, they have to send that information to Earth. It has to go through some processing to Earth, and then we get it. And then once we get that information, that's when we start the planning for the next day. So that's our shift start times actually vary daily. So yesterday we started at 10:30. Today we're starting at 8. And that's because when are we getting the data from the previous day that'll help us start planning our day to day.
Thank you for sharing all that, because it's very interesting. It's impossible for regular guys to understand how you work at NASA with this huge project. Elyse, thank you so much for being here. Thank you for sharing all this. One final message or advice you want to share with our students, those normal students that are struggling with maths and science just like you did, something to encourage them to go for science, to go for whatever their vocation is. Maybe it's arts, maybe it's science, maybe it's math. What would you say to them?
I would say do the things that make you happy, because if you find you're excited about something, it's going to make it easier when you hit the hard problems. And just because it makes you happy does not mean it's easy. So just because you like science doesn't mean you're going to get the perfect grade. And honestly, that's kind of boring if you get the perfect grade in everything, right? It's the thing that's going to challenge you throughout your career is what you want to be interested in. I will also say, you don't have to know everything right now. You don't have to know what you're going to be doing in the future today. I didn't know what career I wanted. I knew that pursuing math was going to keep opportunities open for me, but I didn't know where I wanted to wind up. And if I thought I needed to make that decision, I probably wouldn't have wound up at JPL. I didn't even know it existed. I didn't even know this was an opportunity. I would have closed out pathways that I didn't even know were there. So it's really about trusting yourself, giving yourself patience, and it's okay if you change your mind and change your path, and then you work hard towards that, and you work hard towards that new path, and you work hard towards understanding the challenges. But if it's something you're passionate about, it does make it so much easier to do.
Thank you. Thank you for that, Elyse. It has been a great pleasure. Thank you again for your time and sharing all your experience. Well, UPAEP, Prepas UPAEP, this is the very end of our STEAM week. We hope you have enjoyed all conferences and activities that all of our schools have been implementing over the week. This is just the beginning of a continuous and ongoing process of research and thinking what the right pathway is for me. Maybe it's science, maybe it is technology, math, arts, social sciences, humanities. We have right here in the UPAEP several options for you. It's just about get in touch with your teachers so we can advise and provide guidance in this process of deciding what is the right fit for me. Thank you for all the organizers of this huge project of STEAM Week. And I hope you can go back to the conferences. You can find the recordings in the YouTube channel of Prepas UPAEP. You can share these recordings with your family, friends, brothers, sisters, because those are great resources to understand about the value and impact of STEAM in our lives. Thank you so much for your attention and have a great day.
Eres acción que transforma. Explora el mundo y haz lo tuyo. Responde a tus inquietudes, abriendo posibilidades. Crea a través de tu talento, convirtiéndolo en baile, en música, en una expresión viva. Innova con conocimiento y determinación, buscando soluciones, impulsando tu vocación. Emprende tus ideas, dándole vida a tus sueños, convirtiendo tus planes en hechos. Lidera para transformar tu entorno, aplicando tu conocimiento y generando cambios sociales. Comparte el espíritu ágil. Vive UPAEP, la Universidad Transformadora.